Close your eyes and let your breathing slow. Feel the weight of your body sinking into softness as the day's tensions melt away. Tonight, we're going to drift through the cosmos together, exploring our galactic neighbor floating peacefully in the darkness of space. The Andromeda Galaxy has been watching over Earth for billions of years, a silent companion in the night sky, and tonight, its gentle light will guide you into the deepest, most restful sleep. Let the vastness of space remind you of how small our worries are, how temporary our troubles, and how beautifully insignificant we are in the grand cosmic dance. As we journey through the stars tonight, allow each fact, each image, each celestial wonder to carry you deeper into relaxation, into peace, into perfect, undisturbed sleep, discovery, and early observations. Let's begin our journey by traveling back in time to a night over 1,000 years ago in the ancient city of Isfahan, where a Persian astronomer looked up at the heavens and became the first person to record what would eventually be known as the Andromeda Galaxy. Picture that scene in your mind. Feel the cool desert air. Imagine the absolute darkness of a world without electric lights, where the stars blazed with an intensity we can scarcely imagine today. In the year 964, a man named Abd al-Rahman al-Sufi sat beneath those pristine skies, carefully documenting every point of light visible to his naked eye. Al-Sufi was a nobleman and astronomer who served at the court of the Buyid dynasty, and his life's work was to create the most comprehensive star catalog the world had ever seen. Night after night, he would observe the heavens, comparing what he saw to the ancient Greek star charts created by Ptolemy centuries before. Al-Sufi didn't just copy the old observations. He verified them, corrected them, added his own discoveries, creating a masterpiece known as the Book of Fixed Stars. In this remarkable work, which took years of painstaking observation to complete, Al-Sufi described what he called al-Latka al-Sahabiyya, which translates beautifully to the little cloud or the nebulous smear. He saw it positioned near the constellation of Andromeda, but interestingly, Al-Sufi also referenced Arabic constellation traditions, describing this fuzzy patch as appearing before the mouth of a large fish. Ancient Arab astronomers saw the stars differently than their Greek counterparts, imagining fish swimming through the celestial ocean where others saw a chained princess. This little cloud that Al-Sufi recorded was, of course, the Andromeda Galaxy, though he had no way of knowing that this faint smudge contained 1 trillion stars, each perhaps hosting their own planets, their own stories, their own silent cosmic mysteries. What's particularly soothing to contemplate is that this observation means humans have known about Andromeda for over 1,000 years. For more than 10 centuries, people have looked up at that same patch of sky and noticed that gentle glow. Al-Sufi's careful documentation preserved this knowledge, and his book became one of the most important astronomical references of the medieval period, copied and recopied by hand, its illustrations varying slightly from manuscript to manuscript but always showing that little cloud in the mouth of the fish. The most ancient surviving copy of Al-Sufi's work resides today in the Bodleian Library at Oxford, a manuscript dating from the years 1009 through 1010. In its pages, you can see illustrations of the constellation, and there, marked with dots to indicate a nebulous object, is the Andromeda Galaxy, recorded with pen and ink over 1,000 years ago. It's oddly comforting to think about those medieval scribes carefully copying these star charts, generation after generation preserving this knowledge, never knowing that they were documenting a galaxy, an island universe containing hundreds of billions of suns. What makes Al-Sufi's observation even more remarkable is that ancient Greek astronomers, despite their sophistication and careful sky surveys, never mentioned the Andromeda Galaxy. Ptolemy, whose Almagest formed the foundation of Western astronomy for over 1,000 years, recorded several nebulous objects including the double cluster in Perseus and the beehive cluster in Cancer, but somehow he missed Andromeda entirely. This remains one of astronomy's pleasant little mysteries. The galaxy would have been just as visible in ancient Greece as it was in medieval Persia. Perhaps it was overlooked, perhaps it was noticed but not deemed worthy of recording, or perhaps references to it were lost in the centuries between Ptolemy's time and our own. After Al-Sufi's observation, the Andromeda Galaxy drifted through human consciousness as a barely noticed oddity for centuries. Medieval European astronomers called it simply the Little Cloud when they encountered references to it in Arabic texts that made their way westward. It existed in that comfortable space of things we notice but don't particularly wonder about, like a familiar face in a crowd that never quite demands full attention. Then, in the early 17th century, something extraordinary happened. An invention appeared that would forever change humanity's relationship with the cosmos: the telescope. And in December of the year 1612, a German astronomer named Simon Marius turned his telescope toward Andromeda and became the first person to observe it through magnification. Imagine his surprise when, instead of resolving into distinct stars as other nebulae had done through Galileo's telescope, this object remained stubbornly fuzzy, glowing with an eerie, diffuse light. Marius described what he saw with beautiful, poetic language. He wrote that Andromeda appeared like a candle seen through a horn, capturing perfectly that strange quality of the galaxy's light, that milky, translucent glow that refuses to sharpen into points. On the night of December 15th, 1612, Marius recorded his observation in detail, noting its position near the third northern star in Andromeda's girdle, describing how it appeared visible to the naked eye as a faint nebula, but through the telescope revealed only glimmering rays, which are the brighter the closer they are to the center, with no individual stars visible as he had seen in other nebulous objects. Marius's observation is particularly interesting because he wondered whether this might be a new star, a nova that had recently appeared. He expressed surprise that the great Tycho Brahe, who had meticulously catalogued star positions with unprecedented precision just a few decades earlier, had somehow failed to record this object despite noting other stars in the same region of sky. Of course, the Andromeda Galaxy wasn't new at all. It had been there all along, quietly shining across 2.5 million light-years of space, its light traveling for millions of years to reach human eyes. For the next century and a half, Andromeda remained classified as a nebula, a word that simply means cloud in Latin. Astronomers assumed it was a cloud of gas within our own Milky Way, perhaps a region where new stars were forming, or maybe a far-distant star cluster whose individual members couldn't be distinguished even through telescopes. The French astronomer Pierre-Louis Maupertuis made an interesting conjecture in 1745, suggesting that perhaps this nebula might be an island universe, a galaxy separate from our own, but his idea was considered highly speculative and didn't gain much traction. In 1764, the famous comet hunter Charles Messier was systematically cataloging objects in the sky that might be confused with comets. He wanted to create a reference guide of fuzzy things that didn't move, so comet hunters wouldn't waste time observing them. On the clear night of August 3rd to 4th, 1764, Messier turned his telescope toward Andromeda and added it to his growing catalog as the 31st entry. Messier 31, or M31, a designation by which it's still known today. Messier, somewhat ironically given Al-Sufi's earlier observation, credited Simon Marius with the discovery of this object, apparently unaware of the Persian astronomer's work from 8 centuries before. In his notes, Messier described examining the beautiful nebula with care as Andromeda crossed near the meridian, documenting its appearance and position. This cataloging might seem mundane, but it was actually quite important. Messier's catalog became one of the most widely used astronomical references, and his systematic approach to documenting these objects helped standardize observations and allowed astronomers across Europe to easily identify and discuss the same celestial features. As decades passed and telescopes improved, astronomers began noticing more details in the Andromeda Nebula, as it was still called. William Herschel, perhaps the greatest observational astronomer of the 18th century, noted in 1785 that Andromeda's core had a faint reddish hue. Herschel believed that Andromeda was the nearest of all the great nebulae, and based on its color and brightness, he attempted to estimate its distance. His calculation was wildly wrong by modern standards. He guessed it was no more than 2,000 times the distance to Sirius, placing it at roughly 18,000 light-years away. This underestimate is completely understandable given the tools and knowledge available at the time, and it's actually rather charming to think about Herschel carefully observing and measuring, coming up with a number that seemed reasonable based on what was then known, never imagining the true mind-boggling distance. The 19th century brought new tools and new understanding. In 1864, William Huggins pioneered the use of spectroscopy in astronomy, pointing his spectroscope at Andromeda to analyze the light it emitted. What he discovered was puzzling and profound. Unlike gaseous nebulae, which showed bright emission lines characteristic of glowing gas, Andromeda's spectrum displayed a continuous range of frequencies crossed by dark absorption lines. This was the signature of starlight, the same type of spectrum produced by individual stars. Huggins had proven that Andromeda was stellar in nature, composed of stars rather than glowing gas, though what this meant for its place in the universe remained unclear. In 1885, astronomers observed what they called a nova in Andromeda, a star that suddenly brightened dramatically. At the time, they didn't understand the distinction between what we now call novae and supernovae, and because Andromeda was assumed to be relatively nearby within our galaxy, the extraordinary luminosity of what was actually a supernova didn't alert them to the object's true distance. 3 years later, in 1888, Isaac Roberts took one of the first photographs of Andromeda, revealing a beautiful spiral structure that had been difficult to perceive through direct telescopic observation. This spiral form was stunning and mysterious, leading some astronomers to speculate that these spiral nebulae might be solar systems in the process of formation, vast whirlpools of matter condensing into planets and suns. The early 20th century would bring revolution and revelation, but for now, as you lie here relaxing, imagine all those patient astronomers across the centuries, sketching and measuring, photographing and cataloging, slowly accumulating observations, each one adding a tiny piece to a puzzle whose full picture they couldn't yet see. Feel yourself drifting back through time, through those clear observing nights, through the quiet satisfaction of careful documentation, through the wondering and the mystery, and let that sense of patient discovery carry you deeper into rest. The grand scale and distance. Now let's drift into one of the most wonderfully humbling aspects of the Andromeda Galaxy. Its tremendous distance from Earth and what that distance really means. Close your eyes and try to comprehend, really comprehend, what it means when we say that Andromeda lies 2.5 million light-years away from us. Let that number wash over you, soothing in its incomprehensibility. A light-year is the distance that light travels in 1 year, and light is the fastest thing in the universe, racing through space at 186,000 miles per second. In a single second, a beam of light could circle the Earth more than 7 times. In 1 year, light travels roughly 5.9 trillion miles. Now multiply that by 2.5 million, and you begin to approach the distance to Andromeda. The number is so vast as to be essentially meaningless to human intuition, yet we can state it clearly. Andromeda is approximately 2.54 million light-years away, though measurements vary slightly depending on the method used. Think about what this means for the light you would see if you looked up at Andromeda tonight. That faint glow that reaches your eyes left Andromeda 2.5 million years ago. When that light began its journey, our planet was in the middle of the Pleistocene epoch. Early human ancestors were just beginning to use primitive stone tools. Saber-toothed cats prowled the earth. Mastodons and mammoths grazed across continents. That photon that tickles your retina tonight has been traveling through the void of space longer than humans have existed as a species. This creates an almost magical disconnect between observation and reality. When we look at Andromeda, we're not seeing it as it is now in this present moment. We're seeing it as it was when our ancestors were still figuring out how to nap flint. We're looking into the deep past, witnessing ancient starlight that has crossed an almost incomprehensible gulf to reach us. Similarly, if there were astronomers on a planet in Andromeda looking back at our Milky Way through powerful telescopes right now, they wouldn't see Earth as it is today. They would see our planet as it was 2.5 million years ago. They would see no cities, no civilization, no evidence that intelligence had yet evolved here. Just a blue-green world with abundant life but no technology to advertise its presence. The measurement of Andromeda's distance represents one of the great triumphs of 20th century astronomy. For decades, a fierce debate raged among astronomers about the nature of spiral nebulae. One camp, led by Harlow Shapley, believed that the Milky Way was the entire universe and that these nebulae were simply features within it. The opposing camp, championed by Heber Curtis, argued that spiral nebulae were actually separate galaxies, island universes far beyond the boundaries of the Milky Way. This disagreement came to a head in 1920 at what became known as the Great Debate, a formal discussion between Shapley and Curtis about the scale of the cosmos. The debate wasn't definitively settled until 1925 when Edwin Hubble, working with the massive 100-inch Hooker telescope at Mount Wilson Observatory, managed to identify individual stars in Andromeda. Among these stars, he found several Cepheid variables, a special type of star whose brightness pulsates in a regular, predictable pattern. Thanks to the earlier work of Henrietta Leavitt, who had discovered the relationship between a Cepheid's period and its intrinsic brightness, astronomers now had a standard candle for measuring cosmic distances. By measuring how bright these Cepheids appeared and comparing that to how bright they actually were, Hubble could calculate how far away they must be. His results were revolutionary and mind-expanding. The Cepheids in Andromeda were far too distant to be within the Milky Way. Overnight, Hubble's measurement expanded the known universe by orders of magnitude. The Milky Way was suddenly revealed to be just one galaxy among multitudes, and those fuzzy spiral nebulae were shown to be galaxies themselves, each containing billions of stars, scattered across a cosmos far vaster than anyone had imagined. Since Hubble's initial measurement, astronomers have refined and improved the distance measurement to Andromeda using various techniques. In 2004, researchers using Cepheid variables arrived at a distance of 2.51 million light-years, with an uncertainty of plus or minus 0.13 million light-years. In 2005, the discovery of an eclipsing binary star system in Andromeda provided another method for measuring distance. This binary consisted of two hot blue stars, types O and B, which periodically eclipsed each other from our perspective. By carefully studying these eclipses, astronomers could determine the star's properties and from there calculate the distance to Andromeda with remarkable precision. Multiple subsequent measurements using different methods have all converged on roughly the same answer. Andromeda is approximately 770 kiloparsecs from Earth, or about 2.5 million light-years. The consistency of these measurements from different techniques gives astronomers confidence that this number is reliable. But distance is only one aspect of scale. To truly appreciate Andromeda, we need to consider its physical size as well. The galaxy's diameter has been measured and remeasured over the years, and like many measurements in astronomy, the answer depends on how exactly you define diameter. Using the D25 standard, which measures where the galaxy's brightness in blue light drops to a specific threshold, astronomers in 1991 calculated Andromeda's diameter at 46.56 kiloparsecs, or about 152,000 light-years across. However, more sensitive observations have revealed that Andromeda is actually much larger than this. In 2005, observations with the Keck telescopes in Hawaii revealed a tenuous halo of stars extending far beyond what had previously been considered the galaxy's edge. This discovery dramatically changed our understanding of Andromeda's size. The stars in this extended halo move in disorganized patterns, quite different from the orderly rotation of stars in the main galactic disk, suggesting they were scattered into their current orbits by ancient galactic interactions and mergers. When you include this extended stellar halo, Andromeda's true diameter reaches an astounding 220,000 light-years, making it well over twice as large as our own Milky Way in terms of physical extent. To put this in perspective, if you could somehow place Andromeda side by side with the Milky Way, our galaxy would look like the smaller sibling. The sheer volume of space that Andromeda occupies is difficult to comprehend. It would take light 220,000 years to travel from one edge of Andromeda to the other, crossing a void containing hundreds of billions of stars, nebulae, star clusters, and quite possibly countless planets. From our vantage point on Earth, Andromeda appears remarkably large in the sky despite its tremendous distance. The galaxy's angular size is approximately 3 degrees by 1 degree, which means it covers an area roughly 6 times the diameter of the full moon. If our eyes were sensitive enough to see all of Andromeda's faint outer regions, the galaxy would appear as a huge oval dominating a significant portion of the night sky. However, only the bright central core is visible to the naked eye, appearing as a small fuzzy patch that most people would overlook without knowing where to look. The fact that Andromeda appears so large in our sky despite being 2.5 million light-years away tells you something important. This galaxy is genuinely enormous. This apparent size is not an illusion of proximity. Even across the vast gulf separating us, Andromeda's tremendous physical size ensures that it presents a substantial disk to observers on Earth. Let your mind drift now into the space between here and there, that enormous emptiness that light must cross, taking millions of years to make the journey. Imagine yourself floating in that void, suspended between galaxies, surrounded by almost perfect darkness, punctuated only by the distant glow of stars, so far away they appear as infinitesimal points. Feel the vastness, the silence, the absolute peace of that cosmic ocean. Let the scale of it all remind you of how small and temporary our daily concerns really are, how brief our lives are compared to the light years and eons of galactic time. There's something profoundly relaxing about contemplating such immensity, about feeling yourself to be a tiny part of something so incomprehensibly large. Rest in that feeling now. Let it carry you deeper into stillness, into sleep, into dreams as vast as the spaces between stars. Structure and anatomy. Let's explore the architecture of Andromeda, the grand design of this cosmic city of stars. Imagine floating above the galaxy, somehow able to see it as a whole, viewing its spectacular spiral structure laid out before you like a vast pinwheel frozen in space. Andromeda is classified as a barred spiral galaxy, a designation it shares with our own Milky Way. The term barred refers to a straight structure of stars that runs through the galaxy's center, forming a bar from which the spiral arms emerge. For many years, Andromeda was thought to be a simple spiral galaxy without a bar, but observations in the infrared wavelengths revealed a boxy structure at the galactic center, indicating the presence of the stellar bar. The bar itself is a dynamic structure made up of stars following elongated orbits that collectively create a bar-like appearance. From Earth, we see Andromeda at an angle of about 77 degrees, which means we're viewing it almost edge-on rather than face-on. This orientation makes it somewhat challenging to study the full spiral structure because much of the galaxy appears compressed from our perspective. If we could somehow reposition ourselves to look down on Andromeda from directly above, we would see a magnificent spiral with arms curving gracefully outward from the central bar. But from our actual vantage point, the galaxy appears as an elongated oval. The central region of Andromeda, called the bulge, is where the galaxy's stars are most densely packed. This bulge appears as a bright, yellowish concentration of light, and it's composed primarily of older, cooler stars. These are stars that formed billions of years ago when the galaxy was young, and they've been orbiting the galactic center ever since. Their light now shifted toward the red and yellow end of the spectrum because they've exhausted much of their fuel and cooled down. The bulge has a diameter of several thousand light-years, and within this region, the stellar density is far higher than in the galaxy's outer regions. If Earth orbited a star in Andromeda's bulge, the night sky would be spectacular, filled with thousands of stars bright enough to cast shadows. At the very heart of the bulge, at the absolute center of Andromeda, lies something extraordinarily massive and mysteriously dark. a supermassive black hole. This black hole, designated M31 star, has a mass estimated to be somewhere between 100 million and 140 million times the mass of our Sun. To put this in perspective, if you could somehow weigh this black hole, you would need to pile up the equivalent of 100 million stars the size of our Sun to equal its mass. The black hole itself is tiny in physical size, probably no more than a few 100 million miles across at its event horizon, yet its gravitational influence dominates the central regions of the entire galaxy. The discovery and study of this central black hole revealed something quite peculiar about Andromeda's core. When astronomers used the Hubble Space Telescope to image the galaxy's nucleus in 1991, they found that it appeared double, with two concentrations of light separated by about 1.5 parsecs or roughly 4.9 light-years. First, this was puzzling. Why would the galaxy have two bright centers? Further observations solved the mystery. The brighter of the two concentrations, designated P1, is actually offset from the true center of the galaxy. It's not the nucleus at all, but rather an elliptical ring of older, reddish stars that happen to be orbiting the central black hole in an unusual eccentric orbit. The stars linger at the farthest point of their orbit, creating a concentration that appears brighter than the true center. Meanwhile, the dimmer concentration, called P2, marks the galaxy's actual center and contains the supermassive black hole. Even more remarkably, embedded within P2 is a compact cluster of stars designated P3. This cluster contains many ultraviolet bright A-type stars, young and hot compared to the older stars surrounding them. These stars are orbiting extraordinarily close to the central black hole, racing around it at tremendous speeds. Some of the fastest stars complete their orbit around the black hole in just 100 years, which means they're traveling at roughly 2.2 million miles per hour. At that speed, these stars could circle the Earth in about 40 seconds, and they could travel from Earth to the Moon in just 6 minutes. The presence of these young, hot stars so close to the supermassive black hole presents a fascinating puzzle. Normally, we wouldn't expect to find young stars in such a location. The intense gravitational forces near a supermassive black hole should prevent the gas clouds that form stars from remaining stable long enough to collapse and ignite. The fact that over 400 of these blue stars exist in a disk just 1 light-year across, all orbiting within the black hole's sphere of influence, suggests some unusual stellar formation process occurred here about 200 million years ago. How exactly these stars formed in such an inhospitable environment remains one of the mysteries astronomers are still working to understand. Extending outward from the bulge are Andromeda's spiral arms, though as mentioned, the galaxy's tilted orientation makes these arms difficult to observe from Earth. The arms appear to be somewhat irregular and patchy rather than being smooth, continuous structures. Different observations and measurements have proposed various models for how many arms Andromeda has and how they're arranged. Some researchers suggest the galaxy has 2 main continuous trailing arms, while others propose a more complex structure with multiple arm segments that don't necessarily connect smoothly. What is clear is that the spiral arms are regions where the galaxy's gas and dust are concentrated, and consequently, they're where most active star formation occurs. When you look at Andromeda in ultraviolet light, the spiral arms blaze brilliantly, tracing out rings and patterns of hot young stars that have recently formed from collapsing gas clouds. These regions of star formation appear blue-white in color photographs because young, massive stars emit most of their light at short wavelengths in the blue and ultraviolet portions of the spectrum. Running through the spiral arms are dark dust lanes, regions where dense concentrations of dust obscure the light from stars behind them. These dust lanes trace the areas where gas is dense enough that stars may form in the future, or where stars have recently formed and their stellar winds haven't yet cleared away the surrounding material. The most prominent dark lane in Andromeda runs along the northwest edge of the galaxy's core, visible even in modest amateur telescopes as a shadowy band cutting across the brightness. One of the most interesting features in Andromeda's disk is a ring structure about 10 kiloparsecs, or about 33,000 light-years, from the center. This ring is visible in infrared observations and in maps of the galaxy's gas distribution. It appears to be a region where gas and dust have concentrated, leading to enhanced star formation. The ring isn't perfectly circular or uniform. It has a somewhat lumpy, uneven structure, and it may have been created by gravitational interactions with Andromeda's satellite galaxies, particularly M32, which appears to have passed through Andromeda's disk at some point in the past. The galaxy's disk, when you include the extended stellar halo discovered by the Keck telescopes, extends much farther than the visible spiral arms. Stars in this outer halo show very different motions compared to stars in the main disk. While the disk stars orbit in an orderly fashion, all moving in the same general direction around the galactic center, the halo stars have much more random, chaotic orbits. Some move in one direction, some in another, and many have orbits that take them far above and below the galactic plane. This chaotic motion in the halo is actually evidence of Andromeda's violent past. These stars are thought to be the remnants of smaller galaxies that Andromeda has consumed over billions of years. When a small galaxy falls into a larger one, tidal forces rip it apart, scattering its stars across a much larger volume of space. The orbits of these stars retain some memory of the original galaxy's motion, but they've been so disrupted that they no longer form a coherent structure. Instead, they create streams and shells and diffuse halos around the surviving large galaxy. Observations of Andromeda's outer regions have revealed several such streams, long arcs of stars that trace out the path of ancient collisions. These structures tell the story of Andromeda's growth, how it accumulated mass over cosmic time by consuming its smaller neighbors, growing larger and more massive with each merger. It's a process that continues today, as several small dwarf galaxies are currently falling into Andromeda, being gradually torn apart and absorbed. Throughout all of this structure, from the central black hole to the farthest reaches of the stellar halo, runs dark matter. We cannot see dark matter directly because it doesn't emit, absorb, or reflect light, but we know it's there because of its gravitational effects. The motions of stars in Andromeda's outer regions, the speeds at which gas clouds orbit, the behavior of satellite galaxies. All of this requires much more mass than we can see in the form of stars and gas. Astronomers estimate that Andromeda is surrounded by a massive dark matter halo that extends far beyond the visible galaxy, containing several times more mass than all the galaxy's stars combined. This dark matter halo is crucial to the galaxy's structure. It provides the gravitational scaffolding that holds everything together, preventing the galaxy from flying apart as it rotates. Without dark matter, the stars in Andromeda's outer regions would be moving so fast that they would escape the galaxy's gravitational pull and drift off into intergalactic space. The presence of the dark matter halo keeps everything bound together, a cosmic glue made of something we still don't fully understand. As you contemplate this structure, this vast architecture of stars and gas and invisible matter, let your mind map out the distances, the scales, the intricate organization of this cosmic metropolis. Feel yourself small within this structure, a point of awareness contemplating something so much larger than yourself. There's a meditative quality to this kind of contemplation, a way that understanding structure and pattern can quiet the mind and bring peace. Let that peace deepen now. Let the grandeur of Andromeda's architecture guide you into deeper rest, into a sleep as structured and orderly as the spiral arms tracing their ancient paths through space. The trillion-star population. Tonight, let's count stars. Not literally, of course, that would take far longer than your lifetime, but let's contemplate what it means that the Andromeda Galaxy contains approximately 1 trillion stars. 1 trillion. That's 1 followed by 12 zeros. It's a number so vast that it becomes abstract, losing meaning through sheer magnitude, yet each one of those trillion points represents an actual star, a sun like our own or different, burning through nuclear fusion, warming its surrounding space, perhaps hosting planets of its own. If you tried to count to 1 trillion at the rate of 1 number per second, never sleeping, never eating, never stopping, it would take you more than 31,000 years. The Andromeda Galaxy contains that many stars, and each one is a massive ball of plasma held together by its own gravity, fusing hydrogen into helium in its core, radiating light and heat and energy into the darkness of space. This number, 1 trillion stars, makes Andromeda the most populous galaxy in our local neighborhood. By comparison, our own Milky Way contains somewhere between 200 billion and 400 billion stars, which means Andromeda has roughly twice to 5 times as many stars as our home galaxy. The uncertainty in these numbers reflects the difficulty of counting stars in galaxies. You can't simply look and count them individually. Instead, astronomers must estimate based on the galaxy's total brightness, its mass, and various other indirect measurements. The stars in Andromeda span the full range of stellar types. There are massive blue giants, stars dozens of times heavier than our sun, burning so fiercely that they'll exhaust their fuel in just a few million years before exploding as supernovae. There are medium-sized yellow stars like our sun, stable and long-lived, burning their hydrogen fuel steadily for billions of years. There are small red dwarfs, stars with just a fraction of the sun's mass, burning their fuel so slowly and efficiently that they could shine for trillions of years, far longer than the current age of the universe. Throughout Andromeda's disk, particularly in the spiral arms, you'll find stellar nurseries, vast clouds of gas and dust where new stars are currently forming. These regions appear pink or red in photographs because of the glow of hydrogen gas excited by the intense ultraviolet radiation from newly formed massive stars. One of the most prominent star-forming regions in Andromeda is NGC 206, a vast stellar association containing some of the galaxy's brightest and youngest stars. This region alone spans about 4,000 light-years and contains numerous hot blue O and B-type stars surrounded by clouds of scattering interstellar dust that gives the region a distinctive appearance even in amateur telescopes. The fact that star formation continues in Andromeda means the galaxy is still actively creating new suns, still converting primordial hydrogen into stars that will shine for millions or billions of years. However, star formation in Andromeda appears to be less vigorous than in some other galaxies of similar mass. Observations suggest that the galaxy is transitioning from an active star-forming spiral to a more quiescent state dominated by older stars. This transition may be related to interactions with Andromeda's satellite galaxies, particularly M32, which may have consumed or disrupted much of the gas that would otherwise fuel star formation. Distributed throughout the galaxy, particularly in the halo surrounding the main disk, are globular clusters. These are tight, spherical collections of stars, each cluster containing hundreds of thousands to millions of stars packed into a region just tens of light years across. Andromeda is known to host about 500 globular clusters, far more than the roughly 160 globular clusters orbiting the Milky Way. These clusters are generally very old, containing stars that formed billions of years ago when the galaxy was young. They serve as fossil records of the galaxy's early history, preserving samples of the stellar populations that existed in the ancient past. One particularly notable globular cluster in Andromeda is designated G1, also known as Mayol 2. This cluster is remarkable because it's the brightest globular cluster in the entire local group of galaxies. G1 is so luminous that it can be spotted with larger amateur telescopes despite being 2.9 million light-years away from Earth. The cluster contains about 300,000 old stars and orbits Andromeda at a distance of about 170,000 light-years from the galaxy's nucleus. Remarkably, G1 may harbor a black hole at its center with a mass of about 20,000 suns, an enormous object for a globular cluster and one that hints at the cluster's unusual history. Some astronomers have suggested that G1 might actually be the stripped-down core of a dwarf galaxy that was torn apart by Andromeda in the distant past. Among Andromeda's trillion stars, there are countless dying stars in various stages of stellar evolution. Some are red giants, stars that have exhausted the hydrogen in their cores and expanded to enormous sizes, their outer layers bloated and cool. Some are planetary nebulae, stars that have shed their outer envelopes, leaving behind glowing shells of gas surrounding hot stellar remnants. Some are white dwarfs, the extremely dense cores left behind after medium-sized stars like our Sun have shed their outer layers. These white dwarfs are objects about the size of Earth but containing the mass of a star. Their matter compressed to such extraordinary densities that a teaspoon of white dwarf material would weigh several tons on Earth. Among the most dramatic stellar objects in Andromeda are its supernovae, the catastrophic explosions that mark the deaths of massive stars. Over the centuries of observation, several supernovae have been spotted in Andromeda, providing valuable opportunities to study these cosmic detonations. The most notable was the supernova of 1885, called S Andromedae or SN 1885A, which reached an apparent magnitude of about 6 at its peak, making it briefly visible to the naked eye. For a brief period in August of 1885, this single exploding star was bright enough to be seen without a telescope across 2.5 million light-years of space. The explosion actually occurred about 2.5 million years earlier, of course, with the light just reaching Earth in 1885. But from our perspective, we witnessed a star in Andromeda suddenly brighten to extraordinary intensity before fading away over the following months. More recent supernovae have been discovered in Andromeda using modern automated surveys that repeatedly image the galaxy looking for changes. These supernovae are incredibly valuable to astronomy because they can be used as standard candles for measuring cosmic distances. Type Ia supernovae, which occur when a white dwarf accretes enough matter from a companion star to exceed a critical mass threshold and explode, have remarkably consistent peak brightnesses. By measuring how bright these supernovae appear and comparing that to their known intrinsic brightness, astronomers can calculate precise distances to galaxies. This technique has been used to measure the expansion rate of the universe and led to the discovery that this expansion is accelerating. The stars in Andromeda are not distributed uniformly. As we discussed, the central bulge has a much higher stellar density than the outer regions. In the very core of the galaxy, stars may be separated by just a light year or even less, whereas in the outer regions, stars might be separated by several light years. Our own Sun, located in the suburbs of the Milky Way, is about 4.2 light years from the nearest star, Proxima Centauri. In Andromeda's bulge, stars are packed much more tightly together. If our Sun were located in that dense environment, the night sky would look completely different. Instead of a few thousand stars visible to the naked eye as we see from Earth, observers on a planet in Andromeda's core might see hundreds of thousands or even millions of bright stars filling the entire sky. Different regions of Andromeda have different stellar populations characterized by different ages and chemical compositions. The central bulge is dominated by old, metal-rich stars. In astronomy, metals refers to any element heavier than helium. These stars formed from gas that had already been enriched with heavy elements produced by earlier generations of stars. The spiral arms, by contrast, contain younger, actively forming stars, many of which are metal-poor because they formed from more pristine gas. The halo contains the oldest, most metal-poor stars of all, relics from the very earliest epochs of the galaxy's formation. By studying these different populations, astronomers can piece together the history of star formation in Andromeda. It appears that the galaxy formed in a series of bursts, with major episodes of star formation occurring at different times in its history. The oldest stars in the halo formed over 10 billion years ago, when the universe itself was young. The bulge stars are also quite ancient, mostly older than 8 billion years. More recent star formation has been concentrated in the disk, particularly in the spiral arms. What's particularly soothing to contemplate is that among these trillion stars, there are almost certainly planets. Based on what we've learned about planet formation in the Milky Way, where surveys have shown that most stars host at least one planet, we can reasonably infer that Andromeda must have a vast population of exoplanets. There might be hundreds of billions of planets orbiting the stars of Andromeda. Some would be gas giants like Jupiter. Some would be ice worlds. Some would be barren rocks. And some, almost certainly, would be rocky planets orbiting in their star's habitable zone, where temperatures allow liquid water to exist on the surface. We cannot detect individual planets in Andromeda with current technology. They're simply too far away and too faint. But the statistical likelihood of their existence is overwhelming. Somewhere in Andromeda, there are surely worlds with atmospheres, with weather, with landscapes shaped by geological forces. Perhaps some of these worlds host life. Perhaps on some distant planet orbiting some distant star 2.5 million light-years away, something is looking up at its night sky right now, noticing a faint fuzzy patch of light, unaware that this patch contains our Milky Way, our Sun, our Earth. This is one of the beautiful symmetries of cosmic observation. We look at Andromeda and wonder if anyone there is looking back. If they are, the light they're seeing left our galaxy 2.5 million years ago, showing them an Earth populated by early human ancestors. And the light we're seeing left their galaxy the same amount of time ago, showing us Andromeda as it was in the distant past. We're each looking at the other's ancient history, separated not just by space but by time, two island universes observing each other across an almost incomprehensible gulf. Picture in your mind a random star in Andromeda, one of the trillion. Imagine it as a sun not too different from our own, shining steadily, warming the space around it. Imagine a planet orbiting that star, a world with oceans or mountains or vast open plains beneath an alien sky. The stars visible from that world's surface would be the stars of Andromeda, arranged in different constellations than we see from Earth, telling different stories, mapping different mythologies. And somewhere in that alien sky, if the beings on that world had telescopes powerful enough, they might see our Milky Way, a faint smudge of light in their darkness, never imagining that within that smudge existed billions of stars, including one ordinary yellow star with a small blue planet where beings looked back across the void and wondered. Let this image soothe you now. Let the vastness of Andromeda's stellar population, those trillion suns burning quietly in the night, remind you of the scope and scale of existence beyond our small concerns. Each star is a world unto itself, each potentially surrounded by planets, each contributing its tiny fraction to the galaxy's total glow. And you are here, aware, contemplating these distant lights, connected to them by the simple act of observation, by the photons that crossed millions of light years to reach your eyes. Rest in that connection now, in that quiet communion between observer and cosmos, and let sleep carry you into dreams as numerous as the stars. Satellite galaxies and companions. Andromeda does not drift through space alone. Like a massive ship attended by smaller vessels, the great galaxy is surrounded by a retinue of satellite galaxies, small stellar systems bound to Andromeda by gravity, orbiting their massive parent galaxy in the darkness of space. The two most prominent companions are easily visible in small telescopes and have been known for centuries. Designated Messier 32 and Messier 110, these dwarf elliptical galaxies appear as fuzzy patches near Andromeda's main body. M32 lies just about 24 arc-minutes south of Andromeda's core, appearing as a compact, bright smudge. M110 sits about 35 arc-minutes northwest of the core, appearing more diffuse and spread out than M32. Let's begin with M32, also known as NGC 221. This tiny galaxy is remarkable in several ways. Despite being classified as a dwarf elliptical, M32 is actually one of the brightest and most compact galaxies of its type ever discovered. Its core is extremely dense, with stellar densities reaching levels comparable to the densest globular clusters. The galaxy contains about 100 million to 300 million stars, a tiny fraction of Andromeda's trillion, but still a respectable stellar population for such a compact object. M32's relationship with Andromeda is tumultuous and violent. Evidence suggests that M32 has passed through Andromeda's disk at least once, possibly multiple times. This close encounter would have been catastrophic for M32. the tidal forces from Andromeda's gravity would have ripped away M32's outer layers, stripping off stars and gas and leaving behind only the dense core we see today. In fact, M32 may have once been a much larger spiral galaxy, reduced to its current diminutive state by its interactions with its massive neighbor. The evidence for this violent past is written in both galaxies. M32 shows signs of having lost its outer envelope. It has no dark matter halo, no extended stellar distribution, just the compact core. Meanwhile, Andromeda shows evidence of disruption in its disk structure near M32's current position, including warps and irregularities that suggest gravitational disturbance. The two galaxies are locked in a gravitational dance that will eventually end with M32 being completely absorbed into Andromeda, though this process will take hundreds of millions or billions of years to complete. M32's core harbors its own supermassive black hole, an object with a mass of about 1.5 to 5 million times the mass of the Sun. This is substantially less massive than Andromeda's central black hole, but still represents an extraordinary concentration of mass. The presence of this black hole in such a small galaxy supports the idea that M32 might be the remnant core of a once much larger galaxy. The other bright companion, M110, also known as NGC 205, is quite different from M32 in character. It's larger and more diffuse, containing about 1 billion to 10 billion stars distributed over a more extended region. M110 appears to have experienced some relatively recent star formation, unusual for a dwarf elliptical galaxy. Astronomers have identified regions of young blue stars within M110, suggesting that star formation occurred there within the last few 100 million years, which is very recent in cosmic terms. Like M32, M110 shows evidence of interaction with Andromeda. The galaxy's outer regions appear distorted, stretched by tidal forces from the larger galaxy. Streams of stars extend from M110 toward Andromeda, evidence that the massive galaxy is gradually pulling M110 apart. Over cosmic time, M110 stars will be scattered into Andromeda's stellar halo, adding to the accumulated debris of all the small galaxies Andromeda has consumed over billions of years. Beyond these two prominent companions, Andromeda is surrounded by a large population of smaller dwarf galaxies. Current surveys have identified at least 39 dwarf galaxies that appear to be gravitationally bound to Andromeda, though the exact number depends on how you define satellite galaxy and where you draw the boundary of Andromeda's sphere of influence. These dwarf galaxies range from objects containing millions of stars down to ultra-faint systems containing just a few thousand. Many of them are dwarf spheroidal galaxies, diffuse systems with very low surface brightness, making them difficult to detect. Others are dwarf elliptical, similar to but smaller than M32 and M110. Some of these satellites were only discovered recently through deep photographic surveys that can detect extremely faint, extended objects. The distribution of these satellite galaxies around Andromeda reveals something interesting about cosmic structure. The satellites aren't distributed randomly or uniformly around their parent galaxy. Instead, they appear to be arranged in a vast, thin plane or disk structure, with most of the satellites orbiting within this plane rather than being scattered throughout three-dimensional space around Andromeda. This planar distribution is unexpected and puzzling, as computer simulations of galaxy formation typically predict that satellite galaxies should be distributed more spherically around their parent. The existence of this plane of satellites, sometimes called the Great Plain of Andromeda, is one of several challenges to our current models of galaxy formation. Similar planar structures have been observed around other galaxies as well, including our own Milky Way, suggesting that something about the process of satellite galaxy accretion tends to create these flattened distributions. Exactly why this occurs remains an active area of research. Some of Andromeda's dwarf satellites show signs of recent or ongoing interactions. Andromeda XXXIII, for instance, appears to be in the process of being tidally disrupted, with stars streaming away from the dwarf galaxy's core as Andromeda's gravity tears it apart. Over time, these stars will disperse into Andromeda's stellar halo, becoming indistinguishable from stars stripped from other satellites in earlier interactions. The fate of all these satellites is ultimately sealed. They're all destined to be consumed by Andromeda. The galaxies on more circular orbits will survive longer, taking billions of years to spiral inward and merge with their parent. Those on more eccentric, plunging orbits will meet their end sooner. With each merger, Andromeda grows slightly more massive, adding the satellite stars to its own population. This process of hierarchical merging, small galaxies combining to form larger ones, is thought to be one of the primary ways that galaxies grow over cosmic time. The satellite system provides important clues to understanding Andromeda's formation and evolution. By studying the properties of these satellites, their ages, chemical compositions, star formation histories, astronomers can piece together the history of Andromeda's assembly. Different satellites preserve different pieces of the story, snapshots of different epochs when they fell into Andromeda's gravitational influence. Dark matter plays a crucial role in the satellite system. Each of these dwarf galaxies is thought to be embedded in its own dark matter halo, with the dark matter often outmassing the visible stars by factors of hundreds or thousands. In the smallest, faintest dwarf galaxies, the stars are just tracers of the dark matter, barely visible signposts marking where much larger concentrations of invisible mass reside. Studying the motions of stars in these satellites allows astronomers to map the dark matter distribution and better understand the properties of this mysterious substance that makes up most of the universe's mass. Between Andromeda and our Milky Way, there exist other galaxies that belong to neither system but instead orbit the common center of mass of the two large galaxies. The Triangulum Galaxy, or M33, is the third largest member of our local group and may be associated with Andromeda, possibly orbiting it at a great distance, though its precise orbit and gravitational relationship remains somewhat uncertain. As you relax and let your breathing slow, imagine these satellite galaxies scattered through space around Andromeda, each a small island of stars orbiting the great central galaxy. Picture them slowly spiraling inward, their stars gradually mixing with Andromeda's vast population, ancient systems being absorbed into something larger, their individual identities fading but their substance preserved. There's something peaceful about this slow cosmic ballet, these gravitational dances that play out over hundreds of millions of years, timescales so vast that even the tumultuous violence of galaxy mergers unfolds with what appears to us as gentle, patient inevitability. Let that patience infuse your rest now. Let the slow time of galaxies remind you that there's no rush, that everything unfolds in its own time, that you can simply be here, breathing, resting, drifting towards sleep surrounded by the quiet knowledge of cosmic processes beyond imagining. The Andromeda Milky Way collision. Now let's contemplate something remarkable, something that's simultaneously ominous and wonderful. The fact that the Andromeda Galaxy is heading toward us. Right now, at this very moment, Andromeda is moving through space on a collision course with our Milky Way. Don't worry. This collision won't affect you, or your children, or your descendants for thousands of generations. But about 4 billion years from now, give or take a billion years depending on various unknowns, these two galaxies will meet in one of the universe's most spectacular cosmic events. The discovery that Andromeda is approaching us rather than receding came in 1912 when Vesto Slipher measured the galaxy spectrum and found that its spectral lines were blue-shifted, meaning the light was being compressed to shorter wavelengths by Andromeda's motion toward us. This was quite remarkable because almost every other galaxy we observe shows a redshift, evidence that they're moving away from us as the universe expands. Andromeda is one of the few galaxies close enough that its local motion toward us overpowers the general expansion of space. The speed of approach is about 68 miles per second, or roughly 110 kilometers per second. That might sound fast, and it is by everyday standards, but on cosmic scales, it's actually rather leisurely. At this speed, Andromeda covers about 2.4 billion miles per year, which sounds impressive until you remember that the galaxy is 2.5 million light-years away. Light, traveling at 186,000 miles per second, still takes 2.5 million years to cross the gap. Andromeda, moving about 600,000 times slower than light, will take roughly 4 billion years to close the distance. For billion years from now, Earth will be a very different place. Our sun will be significantly brighter and hotter than it is today, having continued its gradual increase in luminosity as it ages. The Earth's oceans may have boiled away by then, driven off by the increased solar radiation. Life as we know it may have become impossible on Earth's surface. But if by some miracle humans or their descendants still exist and are watching the skies, they will witness an incredible spectacle. The first signs of the approach will be subtle. Andromeda will appear larger in the sky as the distance decreases. What currently appears as a faint fuzzy patch will gradually swell, becoming brighter and more extended, until it dominates a significant portion of the night sky. The galaxy that currently covers an area 6 times the Moon's diameter would eventually span a huge swath of sky, a magnificent spiral looming overhead. As the galaxies draw closer, their mutual gravitational attraction will accelerate the collision. Tidal forces will begin to distort both galaxies, pulling out long streamers of stars. The orderly spiral structures will become disrupted, warped, stretched into peculiar shapes. Simulations of the collision show that the two galaxies will probably make a close pass, swinging past each other, before gravity pulls them back together for a second, more direct encounter. During these passages, the night sky would transform into something spectacular and strange. Stars from both galaxies would be scattered across the heavens. The familiar constellations would be disrupted as new stars from Andromeda intermixed with our sun's neighbors. Depending on where solar systems were located at various stages of the merger, viewers might see two galactic cores in the sky simultaneously, or vast streamers of stars arcing across the celestial sphere. It's crucial to understand, though, that despite the word collision, Individual stars almost certainly won't actually hit each other. Space is so vast and stars are so small relative to the distances between them that even when two galaxies interpenetrate, the stars simply pass by each other. Think of it like two swarms of gnats flying through each other. The gnats might get mixed up and rearranged, but they very rarely collide directly. The same is true for stars in a galaxy merger. However, while stars won't collide, the gas clouds within the galaxies will. When gas clouds from the two galaxies crash into each other, they compress, heat up, and trigger massive bursts of star formation. These collision-induced starbursts would create brilliant new stars scattered throughout the merged system, regions of intense star formation glowing blue-white with the light of millions of newly formed massive stars. The central supermassive black holes of both galaxies will spiral toward each other, eventually merging into a single, even more massive black hole. This merger of supermassive black holes would release tremendous amounts of energy in the form of gravitational waves, ripples in space-time itself propagating outward at the speed of light. If humans or other intelligent beings exist at that time and have gravitational wave detectors, they would record this merger as one of the most powerful gravitational wave events imaginable. Computer simulations of the Andromeda Milky Way collision, using our current understanding of both galaxies' masses, positions, and velocities, suggest that the final result will be a single large elliptical galaxy. The beautiful spiral structures of both galaxies will be disrupted and destroyed, their stars scattered into a more spherical distribution. Astronomers have already given this future merged galaxy a name, Milkomeda, or sometimes Milkdromeda, a portmanteau of Milky Way and Andromeda. Milkomeda will be a giant elliptical galaxy containing all the stars from both parent galaxies, well over 1 trillion stars in total. It will likely be one of the dominant members of the local group, though by that time, the local group itself may have evolved significantly as other small galaxies merge and redistribute. What will happen to Earth during this process? Most likely, our planet will survive the merger unscathed, at least by direct stellar collision. The odds of another star passing close enough to disrupt the solar system are very low, though they're not zero. More likely, the Sun and its planets will simply find themselves in a new location within the merged galaxy, orbiting the new combined center at whatever distance the galaxy merger dynamics leave them. There's even a chance, albeit small, that the Sun could be ejected from the galaxy entirely during the merger. Gravitational interactions during galaxy collisions can occasionally fling stars out into intergalactic space. If this happened to the Sun, future astronomers on Earth, if any exist, would find themselves in a remarkable situation, orbiting a star that drifts alone through the void between galaxies, with the merged Milkomeda Galaxy slowly receding in one direction and the rest of the local group scattered across the sky. The collision with Andromeda won't be the Milky Way's last merger. After forming Milkomeda, the giant elliptical will continue to interact with other galaxies in the local group. The Triangulum Galaxy will likely merge with the system at some point. Various smaller dwarfs will be absorbed. Over tens of billions of years, most or all of the local group's galaxies will probably merge into a single giant system. Meanwhile, on even larger scales, the universe continues its expansion. While galaxies within gravitationally bound groups like our local group can merge, more distant galaxy clusters are being carried away from each other by the expansion of space. Eventually, billions of years in the future, the expansion will have carried distant galaxies so far away and so quickly that their light will never be able to reach us. Future astronomers living in the merged Andromeda Galaxy will look out at a much emptier universe than we see today, with fewer and fewer galaxies visible as more and more of them disappear beyond the cosmic horizon. But these are concerns for the far, far future. For now, Andromeda drifts peacefully toward us through the void, slowly closing a gap that has existed since shortly after the Big Bang, when these two concentrations of matter first began condensing from the primordial gas that filled the early universe. The galaxies have been approaching for billions of years already. They'll continue approaching for billions more. And eventually, inevitably, they'll combine into something new, something different, a galaxy that is neither purely Andromeda nor purely Milky Way but a mixture of both, a new cosmic entity forged from two ancient systems. There's something profound about knowing that our galaxy has a future, that its story isn't static but evolving, that billions of years from now it will be transformed into something new. And there's something peaceful about the timescale involved, about the slow, patient approach of these galactic islands across the void, about processes that unfold over billions of years with unhurried certainty. As you lie here tonight, Andromeda is approaching, closing the distance by about 68 miles every second a tiny fraction less distant than before, inexorably drawn toward a meeting written in the mathematics of gravity and motion. Let that slow approach soothe you, remind you that cosmic processes unfold in their own time, that some things can't be rushed, that patience on a cosmic scale means billions of years of gradual change. Rest in that knowledge. Let it ease you into sleep, into dreams where time moves at galactic speeds and worries dissolve like stars scattering across the night. Scientific discoveries and modern research. The study of the Andromeda Galaxy has been transformed in recent decades by powerful new telescopes and instruments, revealing details that previous generations of astronomers could only dream of seeing. Let's explore some of the remarkable discoveries that modern astronomy has made about our galactic neighbor. One of the most significant advances came from the Hubble Space Telescope, which, freed from the blurring effects of Earth's atmosphere, has captured images of Andromeda at unprecedented resolution. Between 2010 and 2015, Hubble conducted a massive survey project called the Panchromatic Hubble Andromeda Treasury, or FAT. This project created the largest and sharpest photograph ever taken of Andromeda, an image composed of over 7,500 separate exposures. The resulting image is staggering. It contains 1.5 billion pixels and shows a segment of the galaxy about 40,000 light-years across, resolving more than 100 million individual stars. You could zoom into different regions of this image and see stars with incredible clarity, each one a distinct point of light despite being 2.5 million light-years away. The FAT survey has allowed astronomers to study the galaxy's structure in unprecedented detail, tracing out spiral arms, identifying star clusters, mapping dust lanes, and analyzing stellar populations region by region across a huge swath of the galaxy. The survey revealed that Andromeda's disk is filled with complex structure. Rather than smooth spiral arms, the high-resolution images show a chaotic, clumpy distribution of stars and gas. There are regions of active star formation, areas where young blue stars cluster together in associations tens to hundreds of light-years across. There are older stellar populations, cooler red and yellow stars that fill the spaces between the spiral arms. The level of detail is so great that astronomers can study individual stars in Andromeda much as they study stars in our own galaxy, determining their temperatures, brightnesses, ages, and chemical compositions. Spectroscopic observations of Andromeda have revealed important information about the galaxy's chemical composition. By analyzing the light from stars and gas clouds, astronomers can determine what elements they contain and in what proportions. These observations have shown that Andromeda, like the Milky Way, is enriched in heavy elements, the products of nucleosynthesis in earlier generations of stars. Elements like carbon, oxygen, silicon, and iron that were created inside stars and dispersed when those stars died are present throughout the galaxy, incorporated into new stars forming from the enriched gas. Interestingly, there appear to be chemical gradients across Andromeda, with the central regions showing higher metal content than the outer regions. This metallicity gradient provides clues to the galaxy's formation history, suggesting that star formation and chemical enrichment proceeded more vigorously in the inner regions while the outer disk was still relatively pristine. Radio observations of Andromeda have mapped the distribution of neutral hydrogen gas throughout the galaxy. This gas appears in a huge disk extending well beyond the visible star-forming regions, with concentrations along the spiral arms where the gas is dense enough to collapse and form new stars. Surprisingly, the outer regions of this gas disk show signs of warping, bending out of the galactic plane. This warping is thought to result from gravitational interactions with Andromeda's satellites, particularly M31 and M110, whose tidal forces have distorted the outer reaches of the gas disk. Observations in the X-ray portion of the spectrum have revealed a population of X-ray binary systems in Andromeda, objects where a normal star orbits a compact object like a neutron star or black hole. As gas from the normal star falls onto the compact object, it heats up to millions of degrees and emits X-rays. The Chandra X-ray Observatory has identified hundreds of these systems scattered throughout Andromeda, from the bulge to the outer disk. One particularly interesting discovery involves Andromeda's hot gas halo. Observations with X-ray telescopes have detected diffuse, hot gas surrounding the galaxy, a tenuous plasma with temperatures of millions of degrees. This hot halo extends far beyond the visible disk and contains a substantial amount of mass, possibly rivaling the mass of all the gas in the disk itself. The origin and heating mechanism for this hot halo are still being studied, but it appears to be related to feedback from supernova explosions and stellar winds, which heat gas and eject it from the galactic disk into the surrounding halo. Infrared observations have provided another window into Andromeda's structure. Viewed in infrared light, which can penetrate dust clouds that block visible light, the galaxy reveals different structures than in optical images. The Spitzer Space Telescope mapped Andromeda in infrared, revealing the distribution of dust throughout the galaxy and identifying regions of active star formation hidden behind dust curtains. These observations showed the stellar bar at Andromeda's center, a structure that is less obvious in visible light but stands out clearly in the infrared. Recent studies have focused on the stellar halo of Andromeda, that extended envelope of stars surrounding the main galactic disk. Deep photometric surveys have traced this halo out to tremendous distances, finding stars associated with Andromeda more than 200,000 light-years from the galactic center. The structure of this halo is complex, filled with streams, shells, and other substructures that trace the remains of smaller galaxies that Andromeda has consumed. One particularly notable feature is the giant stellar stream, a vast arc of stars that loops around Andromeda, apparently the remnant of a dwarf galaxy that was torn apart by tidal forces. This stream was discovered in 2001 and has since been traced across a huge arc of sky. The stars in the stream all move together through space, following orbits that were set when their parent galaxy fell into Andromeda billions of years ago. Studies of individual stars in Andromeda have revealed surprising details. Hubble observations have identified Cepheid variable stars, RR Lyrae variables, red giants, and other stellar types that can be studied to determine distances, ages, and chemical compositions. By examining these stars, astronomers have constructed a timeline of star formation in different regions of Andromeda, showing when and where stars formed throughout the galaxy's history. The kinematics of Andromeda, the motions of its stars and gas, have been measured using spectroscopy. By observing the Doppler shift in spectral lines from different regions of the galaxy, astronomers can map out how fast different parts are rotating, how much random motion exists, and how the overall rotation varies with position. These observations have revealed that Andromeda rotates differentially, meaning the inner regions orbit the galactic center faster than the outer regions, just as planets closer to the Sun orbit faster than more distant planets. These rotation measurements also allow astronomers to weigh the galaxy. By observing how fast material is orbiting and at what distances, you can calculate how much mass must be present to provide the gravitational force necessary for that motion. These calculations show that Andromeda contains roughly 1.5 trillion solar masses of total mass, including stars, gas, and dark matter. Much of this mass is dark matter in an extended halo surrounding the visible galaxy. The study of novae in Andromeda has been particularly productive. Unlike supernovae, which are catastrophic explosions that destroy a star, novae are smaller eruptions that occur on the surfaces of white dwarf stars in binary systems. As a white dwarf accretes hydrogen from a companion star, this hydrogen builds up on the white dwarf's surface. Eventually, pressure and temperature at the base of this layer become high enough to trigger runaway fusion, causing a sudden brightening. The white dwarf survives this event and can undergo repeated nova outbursts. Andromeda experiences far more novae than the Milky Way, with surveys detecting roughly 30 to 40 nova events per year compared to about 10 per year in our galaxy. This difference might reflect Andromeda's larger stellar population or perhaps differences in the populations of binary stars. By studying these novae, astronomers can learn about binary star evolution and the processes that govern mass transfer between stars. Recent work has also focused on the future evolution of Andromeda as it approaches the Milky Way. Detailed simulations using supercomputers have modeled the merger in increasingly sophisticated detail, predicting what features will emerge as the galaxies collide and how the final merged system will look. These simulations must account for the gravitational forces between billions of stars, the dynamics of gas clouds, the effects of dark matter, and the complex interplay between different components of both galaxies. What's particularly remarkable about modern Andromeda research is the variety of tools and techniques being brought to bear on a single object. Ground-based telescopes, space telescopes, radio arrays, infrared observatories, X-ray satellites. All are observing Andromeda at different wavelengths, each revealing different aspects of the galaxy's nature. By combining observations across the entire electromagnetic spectrum, astronomers can build up a comprehensive picture of Andromeda that would be impossible to obtain from any single type of observation. Future observations promise to reveal even more. The James Webb Space Telescope, with its enormous light-gathering power and sensitivity to infrared light, is beginning to observe Andromeda, potentially resolving even fainter stars and probing deeper into dust-obscured regions. Future 30-meter class ground-based telescopes will provide even higher resolution than Hubble, potentially allowing detailed studies of individual star-forming regions and stellar populations. And as computational power continues to increase, simulations of Andromeda's structure and evolution will become increasingly sophisticated and accurate. As you contemplate all these discoveries, feel the accumulation of knowledge, the patient building of understanding through observation and analysis. Each measurement, each image, each spectrum adds another piece to our understanding of this cosmic neighbor. Scientists across the world, working over decades, have slowly constructed a detailed portrait of a galaxy millions of light-years away, transforming it from a faint, fuzzy patch into a richly understood system. There's something deeply satisfying about this process of discovery, about how careful observation and measurement can reveal such profound truths about the universe. Let that satisfaction settle over you now, that sense of wonder at what human curiosity and ingenuity can accomplish, and let it ease you into a restful sleep filled with dreams of cosmic revelation. How to observe Andromeda yourself. Now let's turn from the grand scientific discoveries to something more personal and accessible. How you can observe the Andromeda Galaxy yourself. Unlike many deep sky objects that require large telescopes to see, Andromeda is visible to the naked eye from any reasonably dark location, making it one of the most accessible galaxies for casual observers. The best time to observe Andromeda depends on your location and the season. For observers in the northern hemisphere, autumn is ideal, particularly from September through November, when the constellation Andromeda rises high in the evening sky. During these months, Andromeda is well placed for observation in the hours after sunset, arcing high overhead from mid-northern latitudes. The galaxy can be seen at other times of year as well. It's visible in late summer evenings and remains observable through winter, but autumn offers the longest and best observing windows. For southern hemisphere observers, Andromeda is more challenging. The galaxy appears relatively low on the northern horizon and is only well placed for observation during the southern spring months, roughly October through December. Even then, it never rises very high in the sky for observers at high southern latitudes, making it difficult or impossible to see from locations south of about 40 degrees south latitude. The first step in finding Andromeda is locating the constellation Andromeda itself. The easiest method is to start with the prominent W shape of Cassiopeia, which is easy to recognize and remains visible throughout the night from northern latitudes. From Cassiopeia, look toward the Great Square of Pegasus, a large square of 4 moderately bright stars. The constellation Andromeda extends from the northeastern corner of this square, forming a long chain of stars stretching away from Pegasus. The key to locating the galaxy is a line of 3 moderately bright stars that form Andromeda's body. These stars, moving from the Great Square outward, are Alpheratz, Merak, and Almach. Start at Merak, the middle star of this chain. If you look slightly upward from Mirror toward the northern sky, you'll see two fainter stars forming a small arc. The galaxy lies near these two stars, appearing as a faint, elongated smudge of light. With the naked eye from a truly dark location, far from city lights, Andromeda appears as a subtle oval patch, brighter toward the center and fading toward the edges. It's surprisingly large. Remember, it spans 6 times the diameter of the Moon, but only the brightest central region is visible without optical aid. The galaxy doesn't look sharp or distinct. Rather, it appears as a gentle glow, a fuzzy patch that's easy to overlook if you don't know where to look. The key to seeing Andromeda with the naked eye is using averted vision. Instead of looking directly at where the galaxy should be, look slightly to the side. The peripheral vision of the human eye is more sensitive to faint light than the central vision, so by looking a bit away from the galaxy, you can actually see it more clearly. This technique takes practice but becomes second nature once you get the hang of it. Light pollution is the primary enemy of galaxy observation. From brightly lit urban areas, Andromeda is invisible to the naked eye, the sky glow drowning out its faint light. From suburban locations with moderate light pollution, the galaxy might be barely visible as a very faint smudge. But from dark rural sites, away from cities and towns, Andromeda becomes prominent and beautiful, clearly visible as an elongated glow in the northern sky. Dark adaptation is also crucial. Your eyes need time to fully adjust to darkness, a process that takes about 20 to 30 minutes. During this time, avoid looking at bright lights, including phone screens and flashlights. If you need light, use a dim red flashlight, which doesn't disrupt dark adaptation as severely as white light. As your eyes adapt, faint objects that were invisible at first will gradually become apparent. Through binoculars, Andromeda transforms into something much more impressive. Even simple 7 by 50 or 10 by 50 binoculars, the common sizes used for casual stargazing, reveal the galaxy as a large, elongated glow with a bright central core. The advantage of binoculars is their wide field of view, which allows you to see Andromeda in context with surrounding stars and even glimpse its companions M32 and M110 in the same field of view. When observing with binoculars, try to brace them against something stable or use a tripod adapter. Binoculars are difficult to hold perfectly steady, and any shaking reduces the amount of detail you can see. A stable view reveals much more of the galaxy's extent and structure. Sweep slowly across the galaxy, taking in its elongated shape and the gradual fading from the bright core to the fainter outer regions. Small telescopes, those with apertures of 3 to 6 inches, begin to reveal more structure. Through a small telescope, the central core of Andromeda appears much brighter and more concentrated. You might glimpse the dark dust lane that runs along one side of the core, visible as a subtle shadow cutting across the galaxy's brightness. The companion galaxies M32 and M110 become obvious, appearing as smaller fuzzy patches near the main galaxy. One important point about observing Andromeda through small telescopes: use low magnification. Many beginners make the mistake of using high power, expecting this to make the galaxy look bigger and brighter. In reality, magnification spreads the galaxy's light over a larger area, making it appear fainter and more difficult to see. Low power keeps the galaxy's light concentrated and provides a wider field of view that can encompass more of the galaxy's extent. A magnification of 30 to 50 times is ideal for most views of Andromeda. Medium-sized telescopes, those with 8 to 12-inch apertures, begin to reveal impressive details. The dark dust lane becomes more obvious, forming a prominent shadow across the galaxy's northwest side. The spiral structure might become faintly visible under excellent conditions, appearing as subtle variations in brightness across the galaxy's disk. The satellite galaxies stand out clearly, with M32 appearing as a bright, compact knot and M110 as a more diffuse, larger glow. Large amateur telescopes, those with apertures of 16 inches or more, can reveal stunning details in Andromeda under dark skies. Multiple dust lanes become visible, tracing complex patterns across the galaxy's disk. Star clouds within the galaxy appear as brighter concentrations. The spiral arms might be glimpsed as faint, curved structures. And with very large apertures and excellent observing conditions, bright globular clusters in Andromeda can be resolved as tiny fuzzy stars. Photography opens up entirely new possibilities for observing Andromeda. Even simple wide-field photographs taken with a camera on a tripod can capture the galaxy, though a tracking mount that compensates for Earth's rotation allows for longer exposures that reveal much more detail. With modest equipment, a digital camera, a tracking mount, and several minutes of exposure time, amateur astrophotographers can capture images showing Andromeda's spiral structure, its dust lanes, and even hints of its outer halo. More sophisticated astrophotography setups using dedicated astronomy cameras and telescopes can produce images rivaling professional observations. Long exposures totaling hours of integration time reveal incredibly faint structures, including stellar streams in the outer halo, the extended disk of M110, and intricate details in the dust lanes and spiral arms. Many amateur astrophotographers have produced stunning portraits of Andromeda that grace astronomy magazines and websites. For those interested in photographing Andromeda, autumn is ideal because the galaxy passes high overhead, minimizing the amount of atmosphere the light must traverse. Clear, moonless nights provide the best conditions. The new moon period, when the moon is invisible and doesn't add its light to the sky, is particularly favorable. Even a partial moon can significantly brighten the sky and reduce contrast, making faint details harder to capture. One of the beautiful aspects of observing Andromeda is that you're participating in a tradition stretching back over 1,000 years, adding your own observation to the countless others that humans have made of this celestial object. When you look at that faint patch of light in Andromeda, you're seeing the same object that Al-Sufi saw over 10 centuries ago, the same object that Messier cataloged, the same object that Hubble studied. The light touching your eyes left that galaxy 2.5 million years ago, crossing the vast gulf of space to reach you at this specific moment. There's something profoundly peaceful about observing galaxies. Unlike planets that move visibly over hours and days, unlike the moon with its changing phases, unlike meteors that streak across the sky, galaxies are patient and constant. Andromeda will look essentially the same tonight as it did last night, as it will tomorrow night, as it will next year and the year after. The changes that matter to galaxies occur over millions and billions of years, timescales so vast that human perception cannot grasp them. When you observe Andromeda, you're seeing something unchanging, eternal in human terms, a fixed point in the sky that will remain there throughout your life and the lives of all your descendants for countless generations. So on your next clear autumn evening, step outside as darkness falls. Look up and find Cassiopeia, trace from there to the great square of Pegasus, follow the chain of stars that forms Andromeda, and look for that faint fuzzy patch near Mirror. Take your time, let your eyes adapt to the darkness. Use averted vision, be patient, and when you finally see it, that ancient smudge of light, pause and consider. You are observing a galaxy, a system of 1 trillion stars, 2.5 million light-years away. The light you're seeing began its journey when our ancestors were just learning to use tools. That light has crossed an almost incomprehensible void to reach your eyes. And in this moment, you are connected to that distant island of stars, linked by nothing more than photons and the simple act of looking up. Let this thought accompany you now as you drift towards sleep. Imagine yourself standing beneath that sky, looking up at Andromeda, feeling the cool night air, hearing the sounds of evening, seeing that faint glow among the stars. Hold that image in your mind as you relax deeper, as your breathing slows, as you surrender to rest. The galaxy is there, whether you're looking at it or not, shining quietly in the darkness, patient and eternal. Let it watch over your sleep tonight, that distant companion, that cosmic lighthouse burning across the void. As we near the end of our journey through the Andromeda Galaxy, let's rest for a while in quiet contemplation of what this great celestial object means for our understanding of the universe and our place within it. Andromeda reminds us that Earth is not alone in the cosmos. Our Milky Way is not the only galaxy. Instead, we inhabit a universe filled with hundreds of billions of galaxies, each containing hundreds of billions of stars, each star potentially accompanied by planets, each planet a world unto itself. The scale is so immense as to be nearly incomprehensible, yet Andromeda makes it tangible. Here is another galaxy, similar to our own, visible in our night sky, a concrete example of the vastness beyond our immediate neighborhood. When we look at Andromeda, we're not just seeing stars and gas and dust. We're seeing history. The light reaching our eyes tonight left Andromeda 2.5 million years ago, meaning we observe the galaxy not as it is now, but as it was in the distant past. This temporal displacement is a fundamental feature of astronomy. The farther we look into space, the further back in time we see. Andromeda is our neighbor in cosmic terms, close enough that the light delay is only a few million years. But this same principle applies to everything we observe. The more distant the object, the older the light, until we look at the most distant galaxies visible to our most powerful telescopes and see them as they were over 13 billion years ago, when the universe itself was young. This means that astronomy is fundamentally a historical science. We can never see the present state of distant objects, only their past. If Andromeda somehow ceased to exist tonight, if some impossible catastrophe destroyed the entire galaxy, we wouldn't know for 2.5 million years. The light from that destruction wouldn't reach Earth until long after humanity has either gone extinct or evolved into something unrecognizable. Conversely, if intelligent beings exist in Andromeda right now and they're looking back at our Milky Way, they're seeing our galaxy as it was 2.5 million years ago, an Earth populated by human ancestors who hadn't yet developed language or technology. Andromeda also teaches us about scale, spatial scale, temporal scale, and the scales of cosmic processes. The galaxy is so large that light takes 220,000 years to cross from one side to the other. It contains 1 trillion stars, each potentially hosting its own system of planets. It's been forming stars for over 10 billion years, more than twice the age of our solar system. And it will continue to exist and evolve for billions of years into the future, eventually merging with our Milky Way to form something new. These scales dwarf human experience. The entirety of recorded human history spans perhaps 10,000 years, a blink of an eye compared to galactic timescales. The largest structures humans have built are tiny specks compared to even a single star, let alone a galaxy. A human lifetime is measured in decades. A galaxy's lifetime is measured in billions of years. This vast disparity in scales can be humbling, can make us feel insignificant, can induce what some have called cosmic vertigo, a dizzying sense of our own smallness when confronted with the immensity of the universe. But there's another way to think about this disparity, one that's perhaps more comforting. Yes, we are small. Yes, our lives are brief. Yes, we occupy a tiny corner of a vast cosmos. But we are also the part of the universe that has become conscious of itself. We are matter that has organized itself into structures capable of looking out at the cosmos and understanding, at least partially, what we're seeing. We are stardust contemplating stars, atoms arranged into patterns that can recognize their own cosmic origins. The atoms in your body were forged in the nuclear furnaces of ancient stars, stars that lived and died billions of years ago. When those stars exhausted their fuel and exploded as supernovae, they scattered their contents across space. That material eventually condensed into new stars, new planets, and eventually, through the long process of biological evolution, into living things, into you. You are literally made of star stuff, recycled stellar material shaped by billions of years of cosmic evolution into a form capable of thought and wonder. Andromeda reminds us that this process isn't unique to Earth or the Milky Way. The same physics, the same chemistry, the same fundamental processes operate throughout the universe. Stars in Andromeda form and die just as stars in the Milky Way do. They create heavy elements through nuclear fusion and disperse those elements when they explode. Those elements incorporate into new stars and planets. And on some of those planets, perhaps, conditions are right for life to emerge. We don't know if life exists in Andromeda. We have no way to detect it from here, but the sheer numbers suggest it's likely. 1 trillion stars. Assuming even a small fraction host Earth-like planets in habitable zones, that's potentially billions of worlds where life might arise. Some of that life might be simple, microbial, basic chemical processes. But some might be complex, intelligent, technological. There could be civilizations in Andromeda right now, beings looking up at their night sky, observing our Milky Way, wondering if they're alone. If such beings exist, they face the same challenge we do. The vast distances between stars make communication, let alone travel, extraordinarily difficult. The fastest spacecraft humans have built would take tens of thousands of years to reach even the nearest stars in our own galaxy, and millions of years to reach Andromeda. Even communication at light speed involves delays of millions of years. If we sent a message to Andromeda tonight, any reply wouldn't arrive for 5 million years. This isolation is a fundamental feature of our universe as we understand it. The speed of light is finite, and it represents an absolute speed limit that cannot be exceeded. This limit ensures that different regions of space remain causally disconnected. Events happening in Andromeda right now cannot affect us, and our actions cannot affect them. We are isolated not by distance alone, but by the structure of spacetime itself. Yet there's a strange connection in observation. When we look at Andromeda, we see it. We observe its light, study its properties, learn its secrets. In some sense, through the act of observation, we are connected to it. The photons that enter our telescopes left Andromeda millions of years ago and have traveled through space to reach us. Those photons carry information about the stars that emitted them, the dust that absorbed and scattered some wavelengths, the motion of the galaxy that Doppler shifted the light. By analyzing those photons, we reconstruct the nature of objects millions of light years away, bringing the distant cosmos into our awareness. And perhaps on some world in Andromeda, other beings are doing the same, their telescopes pointed at the Milky Way, their scientists analyzing light from our galaxy, learning what they can about this collection of stars that appears faint and distant in their sky. We would be observing each other across the void, connected by light, by curiosity, by the simple fact of observation, even though neither civilization would ever know the other existed. There's something beautiful about this idea, about consciousness scattered across the universe, isolated yet connected through observation, each aware of the cosmos around them, each tiny and brief yet capable of understanding. It doesn't matter if we're alone or not in some ways. The fact that we can ask the question, that we can look up and wonder, that we can study galaxies millions of light years away and comprehend what we're seeing, that itself is remarkable. Andromeda will continue its slow approach toward us, closing the distance by about 68 miles each second, patiently drawing near over billions of years. Long after everyone alive today is gone, long after our civilization has risen or fallen, long after humanity itself has either spread to the stars or vanished from existence, Andromeda will still be approaching. Eventually it will arrive, and two galaxies will merge into one, stars mixing and redistributing, a new structure forming from old materials. This is the patient time of the cosmos, where changes unfold over millions and billions of years, where galaxies collide in slow motion, where stars are born and die and are born again from their own ashes, where even supermassive black holes eventually evaporate through Hawking radiation over timescales so long they make billions of years seem like heartbeats. And you are here, now, in this moment, a brief pattern in the flow of matter and energy that is conscious of itself, aware of Andromeda and the billion-year dance of galaxies, feeling the weight of your body, the rhythm of your breathing, the gentle pull of sleep approaching. Hold both thoughts together, the cosmic scale of space and time, and the immediate reality of this present moment. Let the vastness above put your worries in perspective while the warmth and comfort of here and now grounds you in peace. Remember that the same atoms that make up your body have been recycled through cosmic processes for billions of years. You are temporary as an individual, but the substance of you is ancient and will endure. The carbon in your cells was forged inside a red giant star. The oxygen you breathe was created in a massive star that ended its life in a supernova explosion. The calcium in your bones was produced in stellar nucleosynthesis. You are made of the cosmos, and to the cosmos you will return, your atoms eventually dispersing to become part of other structures, other forms, scattered by time into new arrangements. But for now, you are here. You are this particular arrangement of atoms, this specific pattern, this individual consciousness. And you have looked up at Andromeda, you have contemplated its trillion stars, you have understood, at least partially, what you were seeing. You have connected across millions of light years and millions of years of time with another part of the universe. That connection exists now, in this moment, a bridge of understanding spanning the void. As sleep approaches, as your thoughts quiet and your body relaxes completely, let Andromeda be your companion in the darkness. Imagine the galaxy floating peacefully in space, its spiral arms slowly rotating, its stars burning steadily, its supermassive black hole holding everything in gravitational embrace, the whole vast structure drifting through the void like a ship on a dark ocean. It has been there for billions of years and will remain for billions more. A constant presence in the night sky, a reminder of scales beyond human experience, a teacher of patience and perspective. And as you finally surrender to sleep, as consciousness fades and dreams begin, carry with you the image of that distant island of stars, that cosmic companion approaching across the void, that city of a trillion suns shining quietly in the darkness, and know that even in sleep, even in dreams, you remain connected to the vast cosmos of which you are a tiny, temporary, but infinitely precious part. Thank you for joining me on this journey through the Andromeda Galaxy. If you enjoyed this exploration of cosmic wonders, please consider liking this video and subscribing to Deep Science Sleep for more relaxing journeys through the universe. Until next time, sleep well beneath the stars, and may your dreams be as vast and peaceful as the space between galaxies. Good night.